I'm going to be talking about some work I've done with my colleague Shannon Bossard on developing algorithms for processing brand lift studies, making use of attention data, and some smoothing algorithms that can help deal with noise in those brand lift studies. So, as you might imagine, the one of the first things we need to talk about is just what's this data that we're dealing with. So the measurement of the effectiveness of advertising is a field that has many, many different metrics that people look at. In recent years, eye tracking data has become of large interest because we want to know how much people are absorbing the messages that are present in advertising, and that eye tracking is one way of doing this because it's a proxy signal for what we call attention. And this has been enabled by the fact that we've got very, very good eye tracking technologies, both sort of headset technology for people coming into laboratories, but also more passive forms of eye tracking in machine learning driven camera systems that can be on people's own devices if we want to collect information about how people consume media and pay attention to ads. So the kind of overall motivation here is that advertising relies on grabbing the attention of users in order for it to be effective, because it's only once attention has been grabbed can it deliver some kind of message that the user can either remember or have a kind of change in their perception. Now, as a little bit of an aside here, it's worth keeping in mind that when we say attention, we're typically talking about we're in this particular work, we're looking at visual attention, so eye movement as a proxy for what you might broadly call attention, which from the psychological literature is about when the mind is sort of actively processing something. It's worth keeping in mind that visual attention is not the only form of attention, so you can also consider the way that auditory signals can grab your attention. So there's a famous thought experiment in the psychological literature called the cocktail party problem, which is that you can engage deeply in a conversation and that someone will say your name across a crowded room in a cocktail party where you haven't heard anything but kind of background noise, but the pronunciation of your name can pull your attention from that conversation you're in and towards who it is that's saying your name and why. So that process of something grabbing your mental focus is part of the problem of attention. And the reason that we use eye tracking is because the vast majority of advertising is visually based, and measuring the way what people's eyes are focused on is a much, much easier way to go about measuring a proxy signal for what they're paying cognitive attention to. Now, brands also have many ways of trying to understand the effectiveness of a piece of advertising, and foremost among those is some form of brand lift study. So the idea here is that you want to survey panelists once they've been exposed to advertising or not, if they're in the control group, and ask them a variety of questions about their perception of the brand and attitudes towards it, because you're trying to understand if that particular piece of advertising has had any effect on them whatsoever. And so the fundamental idea of this particular piece of research is that we want to see if we can interpret brand studies in a better way by making use of attention data that's obtained from these eye tracking studies. So, as you might imagine, the literature in the kind of space, the intersection between attention measurement and the effectiveness of advertising is quite large. A lot of that work looks at the factors of the advertising or its placement that have some kind of impact on the ability of the ad to grab attention. So things like the color of the advertising, the use of animation or other kinds of images, or the congruence between the product that's being advertised and the content of the media. There is a lot of recent focus looking at this, how particular the duration of attention relates to those brand lift studies. So if I had to sort of distill a lot of the studies from both academic and industry reports, you could sort of say that there's a couple of kind of key insights. First of all, that low amounts of attention can drive upper funnel metrics. but it's generally you see higher amounts required for lower funnel metrics. So actually, for people who are not familiar with these terms, in advertising they generally break metrics of how people perceive a brand into this notion of a sales funnel or a sort of marketing funnel. At the upper end of the funnel are the most general metrics, like is the person even just aware that the brand exists, or do they recall seeing the ad? And as you move down the funnel, you come closer and closer to people choosing to make a purchasing decision. So at the very end, purchase intent or actual sales. And so the kind of key idea here is that those upper funnel metrics can be shifted by small amounts of attention, although that tends to be more to do with the existing size of the brand. So there's some element of previous exposure to advertising from the brand having an influence here. And as we get closer and closer to the purchase decision, generally we see that higher amounts of attention are required because there's more and more cognitive processing required from the consumers to decide that they actually want to buy that brand. Now, one of the interesting things about those upper funnel metrics, right, the broadest possible metrics of brand impact, is that they're actually largely involuntary, right? People don't have a choice over whether or not they become aware of a brand or recall seeing it. These are kind of passive memory functions, and it doesn't require kind of active cognition from the consumer to change an attitude for these things to be shifted. So in general, we should expect that the relationship between these upper funnel metrics and attention should be monotonic. And sort of to put this another way, we have no way of conceiving how more attention paid by someone could make them less aware of that brand, right? It could have no effect whatsoever, but we can't conceive of a way that it actually makes them less aware of the brand. And so one kind of quick summary of this entire piece of work is that we want to exploit that potential fact to help us process some of the noise and some of the problems we see in brand lift study data. So that's kind of a reasonable segue to talk about what those brand lift study problems are. There's many of them. It's typically self-report data, which has its own problems. And it tends to be relatively small samples, sort of 200 to 300 people, because the vendors who do these kind of studies need to find people who are prepared to be paid to take surveys and can be sort of tracked as they move around the internet, so you're able to sort of know whether they've been, or have some idea of whether they've been exposed to a particular ad or not. But there are other confounders in this whole process, and the first of all, that attribution of people to a control and exposed group is actually stochastic. It's not perfectly deterministic, because the algorithms used, whether it be sort of cookie-based or some kind of digital fingerprint that we use to basically determine if someone was exposed to an ad, they're not perfect, right? They're probabilistic, so we don't get that separation between control and exposed is a little bit noisy. And furthermore, even if that separation of control and exposed was perfect, there are still a whole bunch of other confounders that can contribute to this problem. So we know that panelists have unknown levels of exposure to other kinds of advertising by the same brand or other brands, whether it be on billboards and so other kinds of outdoor advertising or radio ads. It's not the case that specific piece of digital advertising we're looking at is the only bit of advertising in that product category that the user has been exposed to, and we actually don't know the extent of that prior exposure for the panelists both in the control and the exposed group. So many sources of noise, and so we're looking for ways to mitigate the impact of that noise when we're processing this data. So the core idea of this paper is that we're going to exploit that psychological constraint that we think that the relationship between attention and upper funnel metrics should be monotonic to smooth some data that comes through in this noise. So in this particular slide here, I'm just showing you a schematic representation of what the monotonic smoothing algorithm looks like. There is some pseudocode in the paper that gives a little bit more detail, but the basic idea is pretty easy to follow. On this sort of, at the top of this, I'm showing sort of the same data across multiple stages of this smoothing algorithm. At the very top, we see sort of the raw data as it's come in. On the x-axis, we have the attention time, and on the y-axis, we have the percentage of people who responded affirmatively to whatever the brand study question was. So let's say, for the sake of argument, this is a question about awareness. Each of the dots corresponds to a group of panelists who paid similar amounts of attention to that particular ad. So we take the average amount of attention of the people within the group as the kind of the attention value for that block, and then it's basically the proportion of those people that answered positively gives us our value on the y-axis. Now, you can see that in general it's kind of moving up and to the right, but it's a little bit noisy. There's kind of movement up and down, and our general assumption here is that because we expect the fundamental process to be monotonic, that up and down volatility is due to the sources of noise that we discussed previously, rather than being a representation of the true underlying phenomenon. So we're going to smooth out that noise, and the reason we do it in several steps is because the process of kind of doing the actual monotonic smoothing gradually upwards is slightly more computationally complex than computationally complex, and we want to minimize the number of steps that we have to, the number of data points we process at that part. So what we effectively do is smooth the data downwards from the top first. So we find the highest point observed, and then merge all of the records from that point forward to get kind of a plateau at the very top. Effectively the maximum observed lift we're expecting to see. Then we smooth forwards from the bottom, where we take the zero attention records and usually the control records as well, and smooth them forward so that any time we see a drop in the outcome, we're assuming that that's just random sampling from the true control. So in a sense, we're saying we're creating a new synthetic control where it says anything that's below the threshold of attention required to get lift is effectively the same as being not exposed to the ad at all. So we smooth all of that data together, and then the final step is where we sort of generate this gradual stepping up function, basically moving forward anytime we see a point that's below the current maximum outcome. We then merge that data back to create a sort of intermediate plateau, and then continue forward. So that's the kind of the fundamental idea of the monotonic smoothing algorithm. And because we want to compare that with other potential algorithms to sort of benchmark it, we took two very general approaches. The first of all is a maximum likelihood approach, where you basically iterate through the potential thresholds and choose the one with the largest empirical lift. Very straightforward. And a logistic regression, where we basically fit a simple model to predict outcome from the attention amount, and then take the value of attention that corresponds to the steepest part of the sigmoid, effectively saying that's where the model thinks that the kind of shift from the lower point to the upper point is occurring. So in order to evaluate it, we ran simulation experiments on synthetic data, in a large part because in the real world, the brand lift study data we get, we don't actually know what the real cognitive threshold level was where lift actually occurs. We don't have sort of direct access to people's minds. So what we've done instead is simulate data that looks like genuine brand lift study data, but we impose a predetermined threshold. That's one of the parameters of the simulation. We say this threshold is where the outcome shifts from the control distribution to the lift distribution. So the process is fairly simple. We're basically for a given set of parameters, sample respondents from across the potential attention times, and then if that attention is above the predetermined threshold, we draw the outcome from one binomial distribution. If it's below that threshold, we draw it from a different binomial distribution. So this is how we sort of synthesize brand lift study data that has this underlying property of attention affecting outcomes through this sort of threshold point, which creates a step function. And so we've basically here's like the parameters that we're varying in the simulation. and then basically what we're going to do is analyze the performance of the models, our approach, monotonic smoothing, compared to the other two models at sort of different values of these different simulation parameters. So I'm going to show you two plots of results. The first one simply looks at the error in the estimated threshold. So remember, we're trying to recover. The whole purpose here is to identify how much attention is required in order to get that lift from the data. And ideally, we want to be able to take one of these noisy brand lift data sets and determine the true threshold using the algorithm. So first of all, we're looking at across many simulations for a given set of parameters, what's the mean absolute error in our ability to predict that threshold. And we're plotting that against the threshold value here on the far left-hand side. And what you'll see is the MS, or monotonic smoothing, is outperforming maximum likelihood and logistic regression, basically across the board, except for the very last threshold where it's slightly higher than the maximum likelihood. So it looks like if the amount of attention required is very high on the bounds of kind of the maximum expected attention, then the maximum likelihood is going to do a slightly better job. And then the second thing we're looking at is the false negative rate, which is basically how many times the algorithm could not find a threshold even though one exists. What you'll see is the maximum likelihood here has a consistent false negative rate of 0 because it actually always comes out, produces a threshold, whereas we've got a slight, like a very small false negative rate in the monotonic smoothing, because when I showed you that process of smoothing from the top down and the bottom up, sometimes they meet in the middle and say, well, actually, there's no expected lift at all. Now, but in reality, you actually want your algorithms to quite often sort of produce, say, there's no actual lift at all. And so with the corollary to false negative is to look at the false positive rate. So like how often does the algorithm produce a threshold where none exists? And so here we're basically rerunning the experiments, but we're just removing the threshold entirely, and basically regardless of how much attention is given, you're sampling from the same binomial distribution. So it's kind of sort of effectively noisy data that sometimes artificially creates the impression that there is lift. And so what we see here is that the false positive rate is unfortunately high for both algorithms. The maximum likelihood almost always returns a threshold. Monotonic smoothing does slightly better, but in the real world, typically what you would do here is some kind of statistical significance analysis. So you would basically only accept a predicted threshold if it was determined to be statistically significant. Right, so some simple conclusions here. We made a simple observation about the psychological constraints involved in attention and advertising that led to a specific data processing algorithm, a monotonic smoothing algorithm for this particular kinds of data. And we've observed that it can reduce the error in our ability to estimate the threshold at which a lift in attention is actually occurring when we compare it against these two kind of very standard baseline approaches that you might use to do a similar thing. In future, we need to, at the moment, we're only focused on upper funnel metrics. So clearly, it'd be interesting to know if there are any other constraints we can apply to deal with lower funnel metrics. And we also want to be able to mitigate the problems of identifying attention thresholds where none exist. So at the moment, the best we could do is some kind of statistical significance test, but we would like to know if there's some other way of performing that, that sort of discrimination. Thank you for your time. Here is how you can contact with me if you want to get in contact or see other projects that I am working on. I'm happy to take some questions.